Okay guys, today we're doing 5.9 advanced related rates. Let's get started. Okay, first thing is we're going to be going by the same steps, okay? So write these down if you haven't already, and let's go through it. There will be a little bit of a change in some of the steps, but basically the same thing, okay? So first thing, I got 3 example problems for you. Here's example 1. A spherical balloon is being filled up. The surface area has a rate of change of 64 inches cubed per minute. And you know what? I just realized this right here. If it is a surface area, it's not going to be inches cubed, but inches squared. Okay? Inches squared per minute. What is the rate at which the volume is changing at the instant the radius is 2 inches? Okay, so we got some sort of balloon here. Okay, this is me drawing my formula here. The radius is going to be 2 inches. And the surface area, the change in the surface area, which I'm just going to have to denote as ds, and I would call it surface area, dSA over dt. That is going to be changing at 64 pi inches squared per minute. Okay, and we got the radius. Okay, so there's step 1 I drew, and I labeled everything I know. Step 2 would be finding the formula I'm going to be using. It looks like I am trying to find the rate at which the volume is changing. So sometimes, a lot of these times with these formulas, they will give it to you. Here's the formula for volume. Okay, so I'm going to be using that formula because I am going to be looking for the change in volume. Okay, so this is what I am looking for. Okay, and then the step 3 is plugging in any non-changing variables. Well, as you blow up a balloon, the radius of the balloon and the volume of the balloon will both change. So there are none. All variables are changing, so we can skip step 3. Step 4 is take the derivative. So the derivative of this would be dv over dt equals, okay, the 3 comes down, that makes it 12 over 3, which is 4 pi r squared dr over dt. Okay, that's the derivative. Okay, now the 5th step is plug in and get your answer. So it looks like so far it's been easy. Let's plug in and see if we get our answer here. All we need is r and dr dt. Well, we know r is 2, and the change in radius we do not have. It didn't give it to us. Okay, and here's why it's an advanced one. We need to figure out what dr dt is, okay? So based off of some of the stuff that was given to us, we should be able to figure it out. Now, if you noticed, we were given this, but we never used it, okay? So we're going to need to use that in order to solve for dr dt. And I have a formula for surface area. So let's take the derivative of it since we know the change in surface area. Okay, so the derivative of this would be dSA over dt equals 8 pi r dr over dt. Okay, now I do have, this is 64 pi equals 8 pi. The radius is 2, and the change in radius is what we're looking for. Okay, so it looks like this is going to be 16 pi, so we can just divide by it, and we have the change in radius. It's going to be 64 pi over 16 pi. I got the 16 pi because 8 times 2 is 16, okay? And that's the same as 4. So we do have the change in radius now, which is what we needed in order to finish this. So the change in radius is 4 inches per time is being measured in minutes. Okay, so let's plug in our stuff and we should get the answer here. The change in volume is equal to 4 pi. The radius is 2 squared, and the change in radius is 4. Okay, so that would be 4 times 4 times 4 is 64. So the change in volume is going to be 64 pi. Let's make sure we get our units correct. Volume is measured in inches cubed per time. In this case is being measured in minutes. Okay, now I know that you are probably making the assumption here that this 64 pi and that 64 pi came from the same place. That was just a coincidence, okay? It was a coincidence that our change in volume was the same as the change in surface area, okay? That's not always going to be the case. So, and it also don't confuse the units here. Surface area would be inches squared while volume would be inches cubed, which I had originally made that mistake right there. Okay, so there's how you do something where maybe you are missing a variable that you need in order to solve for it. Okay, let's go to example number 2. Okay, a rock company is piling sand into a cone shape. Okay, so I have a cone basically. I've got a cone, and it says if the height is always twice the radius of the cone, so our height here is 2 times r, because that's twice the radius, right? What is the rate of change of the volume? So I'm looking for the change in volume when the radius is 3 yards. So we know the radius is 3 yards. Okay, and the radius is changing at 1/3 yards per minute. So the dr over dt is also known as 1/3 yards per minute. Okay, so I have now done step 1. I drew my picture and wrote down my knowns and my unknown. Okay, step 2 is find the formula. That would be volume of a cone, and it was given to us. That is the volume of a cone. Okay, step 3, plug in any non-changing variables. Well, as you pile sand onto this, the radius is changing and the height is changing, so the volume is also changing. Now, one thing though that I do know is that my height changes in the coordinates to my radius. So what I can do is plug 2r in for h. So we can change our volume formula to be 1/3 pi r squared times 2r instead of leaving it as h. And you'll see why this is going to be a big deal when we start taking the derivatives, okay? So volume is going to be equal to, I can multiply the 1/3 and the 2 to make it 2/3 pi r squared times r is going to be r cubed. Okay, so that's my formula for volume now. Now, if you notice, when I take the derivative, which is my next step, if I would have taken the derivative of this, it would have been product rule, which would not have been a fun product rule. This one is not product rule. It's only based off of one variable. This one should be very easy to take the derivative of. So making sure that they give you stuff like this and plugging them in as the things that you need for that 3rd step, that's important. Okay, step 4, take the derivative. Okay, the change in volume is going to be equal to, this comes down, 6/3 is 2 pi r squared dr over dt. Okay, now do I have everything? I have the radius is 3, and I have the change in radius, which is 1/3. So I do have everything I need. It's going to be 2 pi 3 squared times 1/3. Okay, well, one of those can cancel out with that, and that leaves us with 2 times 3, which is 6 pi, and the volume is being measured in yards cubed over minutes, right? Because the time is in minutes. And there is that problem solved out. So the advanced portion of this one was realizing that height was given as 2r and plugging it into here and simplifying it, okay? Everything else was very similar to the past lessons. Okay, I got one more example. The reason why I have this one as an advanced one is because we will be dealing with angles, okay? And we have not dealt with angles yet in terms of related rates. So a scientist is tracking a missile in the sky with binoculars to find its velocity. The missile is traveling vertically from a launch pad 30 miles away. Okay, so we got some launch pad. We're going to say it's 30 miles away. Okay, minutes. Whoops, sorry. Okay, we got a rocket over here. Okay, here's my rocket. For some reason, rockets always have 3 windows. Okay, and then here is my, I believe it said binoculars. So here's my guy that's tracking it with binoculars. Okay, so we got 30 miles away. The guy's standing. At this certain moment, the angle between the ground and the binoculars is pi/3. Okay, so it's telling me that the rocket's already in the air. So let's imagine the rocket's somewhere up here. Okay, so you got your 3 windows. Okay, it's flying. Okay, his eyesight is looking at it, and the angle between that floor and the man is pi/3 radians. Okay, it says that's changing at 1/10 radians per second. Okay, so remember, we track angles by the by the Greek letter theta, and the change in that angle is going to be d theta over dt. And that's going to be 1 over 10 is what it's telling us, and that is an equal sign right there. 1 over 10 radians per second. Okay, what is the missile's velocity at that moment? Okay, well, the velocity would be how fast it's going up, right? So it's going to be the change in height by time. So let's put a question mark. That's what we're trying to figure out, right? Okay, so we got this is 30. We got everything we need here. Now, that's our drawing. We wrote down everything on here. Step 2 is figuring out what the formula would be. Now, I have angles, so I would hope that you're thinking some trig. Maybe SOHCAHTOA would help us out. And if you don't remember your SOHCAHTOA, its sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, or tangent is equal to opposite over adjacent. Well, I definitely have this 30, which is the adjacent, right? And that's the only thing given to me. But I am looking for the change in height, right? So I'm dealing with the opposite side, okay? So I'm going to deal with adjacent and opposite, which is going to be my tangent. So I'm going to have tangent theta is equal to opposite over adjacent. Okay, and I'm going to leave them in 3 letters here because I don't want to put an O for this or get it confused with H's and stuff. Okay, this is my opposite side, and we're looking for the change in the opposite side, and this is my adjacent side, and that's it. Okay, the change in the adjacent side is 0, right? This is not changing. Okay, so this is an unchanging variable, so in step 3 we can plug it in. So let's go to step 3. We figured out our formula. Now step 3 is plug in any non-changing variables. Theta is changing, opposite is changing, adjacent is not changing. So I'm going to have tangent of theta equals opposite over 30. Okay. Now that's step 3. Let's go to step 4. We take the derivative. The derivative of tangent is secant squared of theta. And then we took the derivative, right? Theta, now so it's going to have a d theta over dt at the end of it because we took the derivative of theta. This was chain rule. Okay, take the derivative of this side. Okay, the derivative would be 1 over 30. And we took the derivative with opposite, right? So it's going to be the change in opposite over change in time, which is what we're looking for. That's going to be the change in height, right? Okay, well, we have everything we need here. Theta is going to be pi over 3. Change in theta is 1/10. And the change in the opposite over time is going to be what we're looking for. So we have secant squared of pi over 3 times the change in theta, which is 1/10, equals 1 over 30 times the change in opposite over change in time. Okay, so now we just need to multiply this over. That would make 30 divided by 10, which is 3. So here, let's go over here, and we will continue to solve it. So we're going to have multiply the 30 over here, and the 10 can divide. So we're going to have 3 secant squared of pi over 3 equals d opposite over dt, which is the change in, that's the velocity of the airplane, of the rocket ship. Okay, 3. Now remember, secant is 2 over square root. It's all being squared, right? That's what that squared means. Is equal to the d opposite over dt. Okay, now pi over 3. That would be your index finger, and secant is the same as cosine, so there is a 1 in there. It's in the first quadrant, so it's positive. Okay, this is just 2 squared, which is 4 times 3. It's 12. Is equal to d opposite over dt. Okay, so that's the velocity of my airplane, but you can't just say 12. It doesn't mean anything. We need to make sure we use the correct units. Opposite, it's being measured in miles, so it's 12 miles per, the time is being measured in seconds. And I know 12 miles per second sounds like a lot, but also remember it's a rocket. It's going into space. These things got to move fast. In order just to get into space, you have to be moving around 7 miles per second. So 12 miles per second isn't a terribly large number for a rocket ship. And that's how you do something like that, okay? That's it.